3, we're going to build on what we learned in the last lesson with exponential functions. And, excuse me, we're going to talk about logarithmic functions. So we got 3 basic things that we want to do with this. We want to be able to solve some basic logarithmic equations. And then also learning target 7, be able to graph logarithmic functions. And then learning target 8, be able to rewrite logarithmic expressions using some properties of logarithms. All right, so getting started here. So just some basics. So the first thing you need to know is that the inverse or the opposite of an exponential function is a logarithmic function. Okay, and so here's one thing that always kind of confused me, or at least logs used to confuse me until I really understood what we would use them for. And once I figured that out, a lot of this stuff started to make sense to me. So, like, remember way back in the day when we would solve like one-step equations? Like if I had 5x equals 25, we would do the inverse operation here. The inverse of multiplication would be division, and we would just divide both sides by 5, and we would get 25. Or sorry, we'd get 5. Um, but when I start to do things like 2 to the x equals 8, well, I don't have any simple inverse operation. I can't divide by 2 to solve for x or to isolate x. I can't subtract 2 to isolate x. I need a new inverse function, like division was the inverse of multiplication, or like subtraction was the inverse of addition. I need a new inverse function to be able to solve for a missing variable. And so ultimately, why would we use logs? To solve for that missing exponent. Okay, and so what we've got is we've got logs. And so here's the thing. Remember, just some simple vocabulary. When you've got an exponent, the number down here, this is called the base. Okay, and so if you had this right here, a to the x equals y, well, and you're missing this base, well, this converts to log base a. So whatever is the base here, it goes down here, and the way that we say that is log base a of y equals x. Okay, and I was always kind of confused. Does the x go here or here? Like, what's going on? Well, remember, x is the whole key to this. Okay, so we're doing a log for the purpose of finding a missing exponent. And so your answer would be that missing exponent. So when we convert from here to here or from here to here, if you remember that this exponent right here is the thing that goes by itself, because again, sometimes these x's and y's will change, and that makes it confusing. But remember, whatever is missing here is going to be your answer here, and that can help you with that conversion. And so over here, you can see all sorts of these conversions. Like 2 to the what equals 8. Well, that's like what we had here. Well, 2 to the 3 equals 8, and that's why you see this 3 is your answer. And of course, there's all sorts of different bases that we might have to work with. Commonly, we work with base 10. In fact, if you have like one of those old Texas Instrument calculators, that's about all you can do is base 10. And so, we think 10 to the what equals 10,000. Well, log base 10 of 10,000 equals 5, because 10 to the 5th equals 100,000. All right, let's move on to some examples here. I guess before that, let's talk about graphing y equals log base b of x. So here's the big deal. If we converted this, it would look like, well, we would say we have this is our exponent. So it's like b to the y equals x. B to the y equals x, which looks weird, right? This function that I would want to graph, that would be the same thing as graphing b to the y equals x, or x equals b to the y. Now, here's kind of one of the bottom line things that we're going to do. We can go ahead and do the inverse. And that might make it easier to graph. It might be easier to graph the inverse. Remember, the inverse, we just switch the x and the y. And so when we switch the x and the y, we wind up with y equals b to the x. Hey, that's just an exponential function, which is what we graphed yesterday. And that's pretty easy with the y-intercept being here and b being the rate. Now, if I do this, if I graph that, that's the inverse, which is not what I want. But what I could do is I could switch the x and the y's after doing this. So kind of do the inverse of the inverse, and that would get me back to graphing this, which would be this. And that's more or less how we're going to graph logarithmic functions, at least by hand without a calculator. All right, so learning target number 6, solve some basic logarithmic equations. So one way or the other, these are all just kind of practice shifting numbers around. None of them are actually like finding a missing exponent. But it's still good practice. Here's what we're going to do. We're going to say, all right, log base x. So my base is x. My missing exponent is my answer. And so that's actually that right there. And then equals 8/27. So when I convert it to this, I wind up with x to the third equals 8/27, and I can solve that. How do we get rid of something to the third power? Well, we take the cubed root, and this will cancel this out. And on the right-hand side, I take the cubed root of this, and I get 2/3. Okay, so that's one pretty simple logarithmic function solved. This one, obviously, the x is in a different spot, but the conversion is still the same. I've got the base, which is 4. The answer here is going to be my exponent, so 4 to the 5 halves equals x. And so, you could do this a couple different ways, but I kind of think of it as the square root of 4. So square root of 4 to the 5th power equals x. And well, the square root of 4 is 2. 2 to the 5th is 32, and that pretty well solves it for us. All right, over here, again, here I got the x in a different place. This time it is the answer. So I do have something. I have the base 49 to the x power equals the cubed root of 7. Well, we've seen stuff like this. We had exponential equations that we solved yesterday or in the previous lesson. And so one of the strategies that we had was try to have the same base. And so we can do that here. I can convert this. Well, let's see. If I go ahead and just cube both sides, that gets rid of the ugly cubed root. So cube this as well. And I wind up with 49 to the 3x. And then over here, I just have 7. I can do a common base. I could say this was 7 squared to the 3x equals 7, or 7 to the 1. And, well, let's see. This would be 7 to the 6x equals 7 to the 1. And now that I got that common base, I can eliminate those, and I get 6x equals 1, which means x equals 1/6. All right, so there's solving some basic logarithmic equations. Let's move on to graphing. All right, so there's quite a bit involved here. But if I start with log base half of x, y equals log base half of x. What I'm going to do is I'm going to convert this to the regular thing. I'm going to say like y equals log base 1/2 of x. And then, well, I've got the base 1/2 to the y power equals x. So these two things are equivalent, but of course this is a little bit weird to graph, and so what I'm going to do is I'm going to do the inverse, because that's a little bit easier to work with. The x and the y are in proper spots. So y equals 1/2 to the x power. And what I'm going to do is I'm going to come up with kind of a table of values for this inverse function. So when x equals 0, y equals 1, and then if my rate is 1/2, well, then I know that I'm going to multiply by 1/2 to get to my next number. So I get 1/2 here. Instead of multiplying by 1/2 to go forward, if I want to go backward, I would divide by 1/2, which would be the same thing as multiplying by 2. So if I want -1, 1 times 2 is 2, -2. 2 times 2 is 4. Okay, so I have some values here for the inverse function, but to get I guess we'll call this y to the -1. If I want the actual values for this one up here, I would just kind of reverse them back. So I'd have x, and this time just regular y. Remember, inverse functions, we just switch the x and the y. So to do the inverse of the inverse, to get my original, I just switch these numbers, and I get 4, -2, 2, -1, 1, 0, 1/2, 1. And these are some legitimate values for this guy right here, which is the same as this guy right here. So I'll plot these points. I get 4, -2, 2, -1, 1, 0, and then 1/2, 1. And hopefully you can see how this gets put together. And my asymptote is the y-axis this time. And I go down like that. All right, let's try it one more time with log base 3 of x. I'll change color here. And so again, we'll convert it here. We'll say 3 to the y equals x. But if I want it in something that looks a little better, I'll do the inverse. So the inverse would be y equals 3 to the x. And let's do an easy table of values for that. So when x equals 0, y would equal 1. And then my rate is 3, so I multiply by 3 to get to the next number. So 2 would be 9. I could divide by 3 to get previous numbers. So -1 would be 1/3. -2 would be 1/9. Okay, but if I want the actual numbers for my legitimate function up here, which represented that log function right there, well, then I can just go ahead and switch these numbers. So when x is 1/9, y would equal -2. When it's 1/3, I get -1. 1 would be 0. 3 would be 1. 9 would be 2. And I've got a table of values that I can graph over here. 1/9 would be -2. So that's right about there. 1/3 would be -1. 1 would be 0. 3 is 1. And 9, which would be way out here, would be 2. And you can see the log function getting graphed right there. All right, we do have some examples here. I think I'll just go ahead and do one of these. They're kind of the same. We'll do the more complex one. You can practice this one on your own. But here we see that we have a shift again, which is something common that we've done all year long. So this number takes it left and right. It's going to be the opposite of the sign. So it's positive, it's going to go left. If it's negative, it's going to go right. This number moves it up and down. It's going to be the same as the sign. If it's positive, it goes up. If it's negative, it goes down. So I'm going to do the same thing that I did last time, except when I'm done, I'm just going to kind of shift it, this time 2 to the left, and then 1 up. So I'm going to pretend for a minute that this is like y equals log base 4 of x. Okay, I forget the shift. I'm going to just apply that at the end. I turn this into 4 to the y equals x. I do the inverse of that, which means y equals 4 to the x. I do a little table of values, so y inverse. And so let's pick some things. When x equals 0, y equals 1, I would multiply by 4 to get to the next number, or divide by 4 to get to the previous number. And in order to get the table of values for my original thing, well, original being this thing without the shift, I've got x and then regular y, and then I just switch these numbers. So I've got 1/4 is -1, 1 is 0, 4 is 1, 16 is 2. Won't be able to graph that. But 1/4, -1, 1, 0, and 4, 1. Okay, now these are the graph of this. If I want to get the original one, I got to shift all these points, 2 to the left and 1 up. So I'll switch colors here. And so I take this point, 2 to the left, 1 up. I take this one, 2 to the left, 1 up. I take this one, 2 to the left, 1 up. And now I can go ahead and graph this function. Kind of connect these dots and move it around there, and that's what it looks like. All right, so that's graphing logarithmic functions. Let's use some log properties to go ahead and just kind of manipulate some of these log functions. So they're very similar to what we've done in the past with exponential rules, so you'll probably recognize those. So if I had log base a of x times y, this would be the same thing as log base a of x plus log base a of y. So when you're multiplying, you add. Let's see, how about when we are dividing? So log base a of x divided by y. Well, you probably remember this from your exponent rules. When you're dividing, with the same base, you subtract. And so that would turn into log base a of x minus log base a of y. We also have the exponent one. So if I have log base a of x, we'll say to the r, okay, this one turns out you can just take this exponent and you can bring it down in front here. And this turns into r times log base a of x. So you use that quite a bit. And then just a couple of other quick things. Log base a of 1, of course, equals 0. You know, a to the what power would equal 0. Would equal 1. Well, anything to the 0 power equals 1, and so that's why that's that. Log base a of a equals, well, let's think about this. A to the what power would equal a? Well, itself, 1. And so there we go. All right, well, let's use these properties to manipulate some of these guys. And maybe we won't do all of them, but we'll do some of the simple ones. So here we've got log base 9 of 15 divided by 7. Well, when you are dividing, you subtract. And so this is log base 9 of 15 minus log base 9 of 7. And there's not a whole lot we can do here to simplify. I mean, we can do some of this stuff on our calculator, and not even yet, because most of your calculators, you would either have to do the change of base, which we'll learn next lesson, or what. So anyhow, we've got that, and that's simplified enough for today's lesson anyway. Here we've got log base 5 to, of radical 8. Well, here's how we're going to get around this one. We can say that this is the same thing as log base 5 of 8 to the 1/2. And now I've got an exponent, or a number to an exponent, so we can use that power rule and bring that 1/2 down front. So I have 1/2 times log base 5 of 8. All right, so took care of that one. Let's see, this one seems reasonable. Let's go ahead and we'll say this one could be rewritten as log base A of m squared to the, I guess we'll write it to the of the 2/3. So it'd be like m squared to the 1/3, multiply those together, and you got 2/3. And now you've got this exponent here, and we'll kind of treat it like this one. And so we would get 2/3 times log base A of m. All right, between these two, I think I'm going to pick this one. So this one's got a lot to it, but what we can do is we'll take this to the nth root and we'll throw that up as an exponent. We'll say log base b of x to the 3rd, y to the 5th, over z to the m, and all this would be to the 1 over nth power. Now I've got this situation where I got to a power, like I did up here and like I did here, so that 1 over n can come out front. So we'll say 1 over n times, and then we've got log base b of, well, this whole mess, x to the 3rd, y to the 5th, over z to the m. Well, we're going to go ahead and kind of take care of all of this stuff kind of in one step. The exponents are going to come out in front. The multiplication is going to add. The division is going to subtract. And so I've got the 1 over n, and then kind of throw all this in parentheses, log base b, well, actually we'll say 3. 3 comes in front. Log base b of x plus 5 log base b of y, and then minus m times log base b of z. Whew. All right. So you can see that the exponents came out front, 3, 5, m, and then the multiplication was addition, the division was subtraction. And now I'll just distribute this 1 over n all the way through to the coefficients. So I have 3 over n log base b of x plus 5 over n log base b of y minus m over n log base b of z. Whew. All right. So that takes care of our 3 learning targets: solving, graphing, and converting. Here's the exercises for you to practice.